Good day, students. It's wonderful to know you are joining me on another episode of Mathematics on School on Air. It's always my pleasure to have you join me on this program. Today we shall continue on our discussion on geometry that we started the previous episode. Remember, on that episode we were cut short by time, and I was trying to give you some explanation about a segment and what a ray is before we were cut short by time on that particular episode. Okay, so we just pick up from that point again, and then I'll quickly have to do a brief recap of what we talked about that day. That a segment or a line segment is the part of a line consisting of 2 points, and then all the points that are lying between those 2 points. So that's what we define a segment to be on that episode. And then you can see that you have a line segment AB there. So if we have any other point lying in between these two lines AB, we still call that like AB segment or a line segment. AB, and then we say an endpoint is a point at one end of a segment or the starting point of a ray, and then that's what we call an endpoint. This, or we have point D as an endpoint, and we said a ray is a part of a line that starts at an endpoint and extends forever in one direction. And then you have an example there, starting from here and moving that way endlessly. You can see it has passed through another point there and then continues moving forever. So that's what we say a ray is. And then we said opposite rays are two rays that have a common endpoint and form a line. So we have an example here. We have an example of 2 points, line, a ray EF moving in this direction and ray EG moving in the other direction, and then point E there forming the common point endpoint for the two rays. So those are what we call the opposite rays in geometry. All right, so let's just move on now and take some further examples on how to identify segments, name, and the rest of them. Okay, so we have an example of drawing segments and rays. Now, this question here is saying that we should draw and label each of the following. Draw and label each of the following: a segment with endpoints M and N. So that's the way the question is. All right, so take your eyes off this because that's the result we're going to have. Now, when you are given a question like that, they are always coming in words like that, at least for beginners. Okay, so a segment with endpoints M and N is what is required of us. So they have told us that we have the endpoint as M and N. So what we do in such situation is to put 2 points M and put point N. This is your pencil, point M, point N. Make 2 points, and then so what you do now is to now join the 2 points with your probably your ruler or any straight edge. So you use it to join the 2 points. So we have segment M and segment MN. Okay, so that's the line segment MN. And then B, we are required to draw and label opposite rays with a common endpoint T. Opposite rays with a common endpoint. So I told us previously that opposite rays always have a common endpoint and then they are going in the opposite direction. So in such case, what you need to just do is make the common point, put your point, and then draw a ray going in one direction, draw another ray from that point going in the other direction. So we have this one, this is the common endpoint, this goes in this direction and this goes the other direction. So we have the question solved there. We have the opposite rays with a common endpoint T. Okay, so that's about that one. And then okay, having said that, okay, check this example out. Draw and label a ray with endpoint M that contains N. Look at that, a ray with endpoint M, and that ray still contains point N, right? So we first of all make this. We start from the endpoint M, then produce the ray. Remember, a ray is a line that starts from an endpoint and extends forever. That's how we define a ray. Start from the endpoint and extends forever. And of course, we can have several other lines in between, several other points, I beg your pardon, within the same ray. So we have the ray with this endpoint M extending forever, and then we just locate an arbitrary point N on that ray. So we have a ray with endpoint M, and that also contains N, but which extends forever. So that's about that particular problem. So I believe you get each up there. All right. So if that is that, let's go quickly to something else. Let's go quickly to something else, and that is with postulates. I told us the other episode that a postulate can also be called an axiom. Okay, and a postulate is just a statement, like a theory, that is accepted without proof. So that's what a postulate is. It's a statement that is accepted as true without any proof. And then postulates about points, lines, and planes help us to describe properties of geometry. So the axioms about lines, planes, points, we have about segments and the rest of them. So help us to describe geometric properties. All right. So let's take a look at some of these postulates. And then these ones we are talking about now, they are postulates about points, lines, and planes. Okay, so the first one here. Now you have to just keep your mind off the numbers. Okay, these numbers I've just put them there as a tag. It doesn't necessarily have to mean that you go ahead and begin to cram. Oh, postulate 1.11 says, postulate 1.1.2 says. No, all you need to do is know what the axioms talked about. You don't necessarily need to begin to cram what is postulate 1, 2, 3, and so on. Okay, so having said that, let's look at what the postulates are all about. Now, the first one here says, through any 2 points, there is exactly one line. Remember, we said postulates are statements that are accepted as true without any proof. Okay, so the first postulate we have is that through any 2 points, there is exactly one line. And that's what we have here. Through any 2 points, that's a point, there's another point, there is exactly one line. Remember, a point is said to describe a position, and then without thickness. They are not expected to be thick, and your line also is not expected to be thick. So by and large, it means that the thickness or the thinness of your point will be about the same thickness or thinness as the case may be with the line. So which means that between the 2 points, there can't be more than a line that will probably lie in between. So that's the first postulate. Through any 2 points, there is exactly one line. And then the second postulate says that through any 3 non-collinear points, there is exactly one plane containing them. Now we are talking about non-collinear. Remember, we've talked about non-collinear before. That is, they are not on the same line. Points that are not on the same line. So through any 3 points that are not on the same line, there is exactly one plane. So that's what we have here. We have points that are not on the same line. They are non-collinear points here, and then so there is only a plane in containing them. Then the third postulate that we have here about lines, points, and planes says that if 2 points lie in a plane, then the line containing those points lies in the plane. If 2 points lie in a plane, then the line containing those points lies in the plane. Okay, so this is a plane. You can see that plane, and then there are these 2 points lying in that plane. So the line that is containing the 2 points will also lie on that, and that is just commonsensical. It's a common sense. It's a logical statement that you can see that if those points are lying on that plane, then the line that is containing the point will also definitely be on that plane. Okay, so that's just about the postulates of points, lines, and plane. All right, so let's take a look at another example of what we've just talked about. Example 3 is about identifying points and lines in a plane. Now the question is, name a line that passes through 2 points from here. Okay, so we have this diagram, we have this plane. And then we have this. Okay, this seems to be, what do you think you can make of that? You see the arrowheads going in different directions. So that means we probably have opposite rays there, okay? But that's not what the question is requiring of us. It is asking us to name a line that passes through 2 points. So we have points X and Y. So we have a line that is passing through. So we say that the line is line X, Y. So we describe the line by just placing the line with the double arrowhead on X, Y written together, the 2 points X, Y written together. So the line that passes through 2 points on this particular plane is line X, Y. Line X, Y, because it's the one that is containing the 2 points X and Y. Is that taken? Okay, so I believe you understand what we are talking about there, how to name the line that passes through 2 points in a given plane. All right, so check this one out. If we are satisfied with that, name a plane that contains 3 non-collinear points. A plane that contains 3 non-collinear points. So we've seen a linear point and we are not seeing non-collinear now. That is, they are not on the same line. All right, so we actually can see that these two are on the same line, but this one is not on the line with them. So we have 3 points that are non-collinear: G, H, and F. G, H, and F. They are all on the same plane, but they are not on the same line. So our possible answer would be G, H, and F. I have said possible answer because the order of arrangement of the points is irrelevant. So you probably have said point F, G, H, or point H, G, F, or point H, F, G. So the order does not really matter. Okay, the only thing you need to know is name the point. So we have point G, H, and F. And sometimes, like I told you previously, that apart from describing a plane by the points that made the plane, the plane can also be given its own name, like we have in this case. This plane is called plane R. You can see that R is not any point on that plane, so it's describing the plane. So we can describe the plane also as a plane R. Plane R. Okay, so the line can be described as, the plane can be described as a plane R rather than saying plane G, H, and F. Okay, so if that is taken, I want us to quickly recall some things about set of equations and then a set of planes and lines that we're going to be having, and then how to deal with them. Now, I've said that you should recall that a system of equations is a set of 2 or more equations that contain 2 or more of the same variables. That's what we call a system of equations. Remember, we've done that when we're dealing with algebraic simplification and then the rest of them. Okay, so the coordinates of the solution of the system always satisfy all the equations in the system. The coordinates in this context is talking about the solution of the set of equations. By the time you put them back in the equations you have, it always satisfies. Okay, so these coordinates also locate the point where all the graphs of the equations in the system intersect. So when we have a set of points in a plane, and then we try to deal with them together. If we have a graph and then you use the coordinates on the graph, there is tendency that we have intersection. So these coordinates locate the point where all the graphs of the equation in the system will intersect. Okay, so talking about intersection, it is the set of all points that contain 2 or more figures have in common. That contains the set of all points that contain 2 or more figures. What 2 or more figures have in common. So the next 2 postulates quickly that we're going to have to take a look at, we'll be talking about the intersection of lines and planes. So we have this one: if 2 lines intersect, then they intersect in exactly 1 point. If 2 points intersect in exactly 1 point. And the second one is that if 2 planes intersect, then they intersect in exactly 1 line. If 2 lines intersect here, they intersect in exactly 1 point. And if two planes intersect, they intersect in exactly one plane. So that is that about the postulates. And then make sure you always use a dashed line to show the hidden parts of any figure that you are drawing. A dashed line will indicate the part of the figure that is not seen. And quickly, we're going to have to take a look at this one. Sketch two lines intersecting in exactly one point. So that's it, a line and another line intersecting at a point here. And then sketch a figure that shows a line that lies in a plane. So we just have a plane. Your plane could look anyhow, and then you have a line there that is lying on that plane. All right, so that's just that. And you can also quickly check this one out, because I told you that you use broken lines, dotted line, to show the hidden part of a line that is not on the plane, shown on the plane. Sketch a figure that shows two lines intersecting in one point in a plane, but only one of the lines lie in the plane. So this is the line that lies in the plane. So you have all the portion of the line in the plane. Now this other line, even though it intersects this one, does not lie on this plane. That's why you see it moving out. So this other part is just put there to show probably the other part of the continuation of this line that is not seen, because this line is not supposed to lie on this plane. So we use this as an imaginary continuation of this line. So it's not to be considered. The lines to be considered here is this and this. All right, so that's the essence of the dotted or the dashed line that you have there. And it's on that note that we are going to have to wrap it up on today's episode of mathematics on School on Air. All right, so before I go today, remember the other time we met, I gave you an assignment to do. I want to say well done to those of you who have done it and they have sent their answers in. I've received them and I say God bless you. Today I expected some more positive results, which I did not actually get from the answers I received. So I will have to send you back home again. Try to do more business-like work on the assignments. Now that you have learned more about intersecting lines and planes that are lying and lines that are hidden from the plane. So you have this set of questions again to go back home and do better job this time, as I'll be waiting to receive your responses, which you will of course send to the address that you have below your screen. So on that note, that I'm going to have to say goodbye on this episode of Mathematics at School on Air. Till I come your way another time, enjoy yourself and God bless you.